Thank you, Oswald. So I think now you can hear me. So guys, I was telling you that it took slightly longer because I had to save the video of the, the first part. Anyway, so we have just shown that the Maxwell equations via the Ampere Gauss law, and it's the same for the Faraday's Gauss law. It's the same exercise. They are Lorentz invariant, so they are covariant. It's, when we say that these equations are covariant, is because they are invariant in the Lorentz transformations. This is something that you'll be hearing throughout the course. When we say covariance, it's because they are invariant and the Lorentz transformations. But there is another invariance inherent to these equations. And does anybody here has an idea what exactly? So it's gauge invariance that we're talking about, and this is a simple. This is going to be a very very simple proof. But before that, let me just say. So now we are talking about gauge invariance. Gauge invariance. This is just a first glance, a very first and simple glance about gauge invariance. And gauge invariance has really, really profound consequences in particle physics. So this is because of gauge invariance that you have gauge bosons. You have gauge bosons. It's because of the existence of gauge invariance. So it's because of gauge invariance that photons and gluons are massless because of gauge invariance. And also gauge invariance is a protecting symmetry. Is a protecting symmetry in the sense that, for example, W and Z bosons have small masses, when we compare to the Planck scale. Small masses when compared, example, to the gut or scales. Because when we say that the mass is small, it's always a matter of small with respect to what. In this case, we are talking about some higher energy scale. So W are small masses because of gauge invariance, basically.
So all the elementary forces are gauge invariant?
Action. Say again, sorry?
All the elementary forces are gauge invariant?
Yes, all elementary forces. I mean, not gravity in the sense.
Linearly, gravity as a gauge invariance. But for general space-time, it's not.
It's more complicated. Yes, that's
it's almost invariant, but
right. Yeah.
But that doesn't conflict with our definition of forces.
What do you mean not conflict with our definition of forces?
The electromagnetic strong and weak force are gauge invariant, but gravity isn't.
Right. So that we know. So let's put the things here. So we know that the strong and the electroweak forces, weak and electromagnetic forces, to be more specific, they result from this gauge invariance principle, and a theory of basically that transforms under any of these forces is clearly gauge invariant. And if you want to break that gauge invariance, we need really to do something to break that, because the symmetry is strong to the point of you having to break it to violate it. So with gravity, I'm not an expert, but it's a different story, as you are saying. And that's one of the debates. Is really gravity a fundamental a fundamental theory. So and now I'm looking to Ilaria because this is exactly one of the things that we are thinking about. So there are elements in gravity that may make us think this is a fundamental, and we need at some point to quantize it and to have a gauge theory of gravity in the same way that we have.
So we are trying to find a gauge theory for quantum gravity.
That's one of the paths, but there is another path, which yes, let's say that conservative if you want to, but there is another one which is let's think that gravity is not fundamental and it's emergent. So an emergent force or an emergent interaction is something that doesn't exist at fundamental level, but exists as a result of other fundamental interactions. And that's the proposal of emergent gravity. For example, there are proposals that saying that gravity emerges from the strong interaction. And what Ilaria wants to study is like the emergence of gravity from like something that's called the fixed off-shell energy momentum conditions. Like basically, you violate the equations of motions off-shell, and but when you fix that, you have a way of inducing gravity, basically of showing up. G mu nu shows up in the equations when you fix those conditions. So, but of course, this is very, very, very poor statement of what this emergent gravity proposals are. But that's exactly the point. We know that the electroweak and the strong forces are clearly gauge theories, and they obey the gauge principle, and we know how to control that.
Gravity. Because I think let's say that the Higgs boson wasn't a force carrier because it didn't have gauge invariance.
Well, not in the sense of he's not a force carrier in the same in the sense of, for example, of the gauge bosons. Yeah. So it participates in interactions, for example, the interactions that give rise to mass of particles. It mediates that interaction. You can read in that way. Exactly. You can read that in that sense. You can say that it's a Yukawa type interaction, but it's not a fundamental. At least from the perspective of the standard model, it's not a fundamental symmetry. It's not a fundamental gauge symmetry. But maybe it has emerged from a fundamental gauge symmetry in a grand unified perspective. That's a different story. Still, the Higgs is not a gauge boson, so it's a scalar. It does not have this protection of its mass by gauge. So this last point here, this point that is here, is one of the nice things about gauge symmetry, gauge invariance. Because a gauge theory protects, so the gauge bosons of a certain gauge theory have a mass protected by the symmetry. And they acquire mass at the scale where that symmetry stops existing, basically when that symmetry is broken, and protects against effects from much higher energies. This is why we have W's and Z bosons at the electroweak scale. But we don't have the same explanation for the Higgs mass. Why the hell is the Higgs mass at the electroweak scale? Nobody knows. It's a scalar. It does not have protection from gauge symmetry. And it can have the Planck scale or some gut scale mass. It should indeed, in the standard model, it should have corrections. This is what is called the hierarchy problem. If you heard about this, is what Marco is leading us towards this, or this discussion is leading us towards the hierarchy problem, because there are fundamental differences between what we call a gauge symmetry and what is a Yukawa, gauge interaction, what is a Yukawa interaction at the level of the standard model. Unless you are able to unify, to embed the Yukawa interactions in a framework that contains all of this information in a single piece, and then things branch out and behave differently. That's a different, and that can be done with extra dimensions. And so, for example, a vector field in 10 dimensions. So a vector, you know, a mu, it has 0, 1, 2, 3. So it has the dimensions of the space-time. So the a mu's have these 4 space-time dimensions. If you go, for example, to 10 dimensions, you have the a mu's in 10 dimensions are vectors with 10. So mu goes from 0 to 9, let's say. What happens is that the 4-dimensional part corresponds to the gauge, to the gauge bosons, the 4-dimensional ones that we know, but the extra 6 dimensions, they and if these extra 6 dimensions are complex, you can say that you don't have 6 extra dimensions, you have 3 complex extra dimensions. So each of these 3 extra components are complex scalars. So you can say that the Higgs bosons results from, this is on an example, I'm not saying this is the theory, but you can say the Higgs bosons, the Higgs, the scalars that we know, and the only one that we know so far is the Higgs boson, it was part of an extra dimensional vector. And in that sense, it was in the primordial, very primordial universe, it was a gauge, part of a gauge boson, but then with compactification and in 4 dimensions, etc., that behaves as a scalar and no longer as a gauge boson. But it was part of a vector or a gauge boson of a more fundamental symmetry. Right? So is it a Osvaldo? Yes.
Also, if you have a mechanism that has the same effect as gauge protection and allows for the Higgs boson to have a small mass, how confident would we, if that were the case, how confident would we be that the small masses of the W1 said would be exclusively because of gauge protection as we know it now, and not because of all these extra effects? Would they share that extra dimensionality?
So there is 2 points here. So when I was talking about this, the Higgs can come from some more fundamental description. This is not telling that the mass is protected. Because as soon as these 10 dimensions, let's say, as soon as they compactify, as soon as you have a separation between a 4-dimensional and the components, the extra dimensional components, which become 4-dimensional scalars, so they become 4-dimensional scalars. The Higgs or even the scalars acquire that mass scale, and that we know has to be above the electric scale. So we maybe will alleviate this problem of the Planck or gut scale, but we still have this compactification scale and the scale where that phenomena happens. However, the gauge part, it still benefits from the protection, and the protection is basically you don't have any radiative effects that can generate you the mass, basically. That's essentially the point.
From self-interaction?
From self, like this, for example, I can write something here for the Higgs. So we have the Higgs mass. So you have the Higgs mass. It's a Higgs mass squared, which is equal to some mh0 squared. So this is a true level plus some delta mh squared. And this delta encodes radiative corrections. And when we go to one loop, for example, you say, for example, at one loop, if it's at one loop, you have something like this. Right? So you have here a quartic coupling here, because this is a quartic interaction here. You will learn this in a bit more detail. So this is a quartic interaction here. Basically, if you zoom in here, if you look only to here, it's a 4. It basically what you have is this. Right? So this is, then you close it. Actually, it's what you're doing.
There's something covering the window.
Not for them.
Not for them, but for us.
Sorry, what?
Those
Zoom.
Right. Yes. So I wanted to put it.
You are probably, but
No, I don't want to do again the
You
same.
can minimize.
Right. I can minimize still.
Yeah.
And delete. Right. So you have this, and this here, this thing is proportional to lambda times, let's say this mass scale. So like this some let's say mu squared. So this mu squared is like the characteristic scale that you have in this loop. Let's say. So what happens is that if lambda is 0, of course you kill these interactions. So you can just say that your couplings are tiny and these contributions don't show up. But within the standard model, it's not really easy to say. We know lambda. Lambda is like almost 1, or it's 1.3, or something like that. It's a sizable coupling. And if you allow this momentum in the loop to go all the way up to the Planck scale, then you have corrections which are of the Planck scale. So which means that this contribution, so here if you have like m Planck squared, here
Contained in that delta stuff.
yes. This delta is delta means like it's a mass. Let's say it's a correction to the mass, but it's a huge correction. What happens is that here the true level mass has to be minus m Planck squared plus some epsilon with epsilon of the order of the electroweak scale. And double boson, for example, yes, and W top Z doesn't matter. So you see what's happening here, and this is a square. These are squared quantities. In fact, let me make the dimensions here. So this is squared electroweak scale, and I will clear right. So this is electroweak. I will write here electroweak scale. So look at what's happening here. You have that mh squared is then equal to minus m Planck plus epsilon plus m Planck squared, which is of course equal to epsilon, which is of the order of m electroweak squared. And we measure this. We measure this the Higgs mass. I'm only talking about orders of magnitude, but the amount of decimal digits that you have to cancel out in this, it's remarkable. So you really have to control these loops. If you have, and this is only true level. If you go beyond true level, this is still huge correction. And then you have to say that these corrections, they happen order by order. So at all orders in perturbation theory. Of course, if you go to extremely high orders, you have further suppression. In fact, here there is one suppression which is like it goes with something like 16 pi squared, and this 16 pi squared is gradually going to having higher powers.
The series expansion has converged.
It converges. The series expansion is convergent, but so this is why we can have this expansion. It's a perturbative expansion. So the parameter is lambda over 16 pi squared, and lambda over 16 pi squared is smaller than 1. So and this guarantees the convergence of this expansion. But still, you need look. Planck is 10 to the 18. Let's put. Even if you are to the gut scale, it's easier. It's also dramatic. 10 to the 16 GeV, the conventional gut scale. So you square this. You have 10 to the 32, and now you want to be left with 10 to the 2. So you need to cancel out 10 to the 32 minus 10 to the 30, something like, well, minus 10 to the 32 plus some tiny difference in the 30th decimal digit. So you see, and you have to guarantee that this happens at all orders. So this is why the existence of the Higgs boson itself is really calling for. It's really something that works extremely. It's annoyingly well how it works in experiments, but it's also something that we really don't understand. We don't understand the fundamental origin of the Higgs boson. Right. So this was just to say that and for gauge bosons is different. In gauge bosons you don't have this sort of things. For gauge bosons,
it's only triple.
yes. Let's say what happens with gauge bosons is that you always have a mass, the mass of the gauge boson, basically there to control the. So the corrections are proportional to the mass itself. See, so that's what happens. And when it goes to higher energies, the mass goes to zero, and then the correction vanishes as well. Let's say. This is in very crude terms. I'm talking in very crude terms. Right now, we wanted to talk about gauge invariance. First, we just said that there are remarkable and very important consequences of gauge invariance. But now, let's just see very trivially what happens. What is a gauge transformation? So we have the freedom to say that the vector, so the electromagnetic field, or this AMUs, so a certain AMU is not unique. We can redefine it as, for example, AMU goes to some AMU prime or A prime mu, which is given by the original mu plus or minus, it doesn't matter as well. I will put plus d mu alpha x. So x is a function of the coordinates. And now it's very simple. So we have the f mu nu, which is equal to d mu a nu minus d nu a mu, and we can simply apply this here and do. So this goes to, so f prime mu nu is going to be d mu a prime nu minus d nu a prime mu, and this is equal to, let's use this here. So we are now using this d mu a nu minus, no, plus, sorry, plus d mu alpha x. So this exactly minus d nu alpha nu, and now minus, exactly, minus d mu alpha x, right? You agree with this?
Yeah.
And since you can commute the derivatives, so the derivatives commute, you can write it simply as d mu alpha nu minus d nu alpha mu plus d mu alpha x minus d mu alpha x, and these two simply vanish. So we have that f mu nu prime equals to f mu nu, and this is because of gauge invariance. So f mu nu is gauge invariant and so is or are the mu f mu nu. So basically the Ampere-Gauss law and this is not zero, sorry, this is, I'll put here just so 4 pi j nu, but maybe more. 4 pi j mu and also the mu f star mu nu equals 0. So we have just proved the covariance and gauge invariance of Maxwell theory, and that's it. This makes it for Maxwell theory. We can now start with the relativistic quantum mechanics, but maybe we have a break, a small break. I think you guys may want to have a short break. So let's just break for 10 minutes, and then we continue after the break. I will pause the recording because what's time. Okay. Right. So let's continue, and we are going to change topic a little bit. Now we are going to revise a bit of relativistic quantum mechanics. So, whom of you already have a lot of experience with the Dirac equation, the Klein-Gordon equation, right? And those online.
A little bit for me.
Sorry?
A little bit for me, actually.
Okay, right.
Some experience.
Okay, so it's because the backgrounds here are a little bit different between all of you, but we will discuss the main, essentially the main things. So let's start. Let's relativistic quantum mechanics. Relativistic quantum mechanics. This is just some sort of a revision again, but of important concepts and things that are going to be useful in what follows. So let's start with first with the Klein-Gordon equation. So you know from your courses of quantum mechanics that if we consider a particle with energy, with kinetic energy, which is given by p squared over 2m, you know from one of the postulates of quantum mechanics that says that physical observables can be represented by Hermitian operators, linear Hermitian operators, in fact. So you can just make this identification saying that E is an operator, which is going to end up being the Hamiltonian, and this can be written as a time derivative dt, and also P, the operator. I will not keep this Hertz operator all the time, but it is just at the moment just to point out that we are talking about operators. And from here you obtain the well-known Schrödinger equation without H bars. I will not put H bars here, but you can write, for example, C equal to p squared over 2m psi, from where you take I d psi dt equal to minus 1 over 2m This is gradient square psi. And this is the well-known Schrödinger equation. This is Schrödinger equation. This equation offers a good description for in the context of non-relativistic quantum mechanics, of course. But if we go to relativistic phenomena, this is no longer a reliable description. So we can do the same exercise here and just use the relativistic energy condition. So we know that energy. So let's do for what about relativistic energies? So let's pick up the energy of relativistic particle, which is given by m squared plus p squared. And in fact, you can write this as e squared minus p squared equal to m squared. And use the same, you just promote these two operators, let's say, and apply it to a certain field phi here. And there is a reason for me to calling phi at the moment. And you can do the following. You just have I d dt squared minus I gradient squared. Now let's apply to phi equals to m squared phi, from where you obtain, you can put outside the minus sign, so we have the 2i squared here, and you can write d2 minus gradient squared phi equal to m squared phi. And finally, so this is the D'Alembert operator. So you can write this as a square. So you can at last write it as follows. Plus m squared phi equal to 0. And this is our Klein-Gordon equation. This is the Klein-Gordon equation. And this was basically from 1926. Just to have a reference for the dates where Klein-Gordon basically developed their theory, and they proposed the Klein-Gordon equation. And this equation is covariant once again. Now let's talk about again Lorentz transformations here, and there will be something important here that will tell us why this equation only applies to scalar particles. It emerges from the covariance of the Klein-Gordon equation that this phi is a scalar, and that is what we want to discuss. So m squared is on its own a Lorentz invariant, so we don't need to do much about it. But about the D'Alembert operator, this is in fact g mu nu d nu, and we can transform the coordinates as we have done in the previous hour. G mu nu And you can write now lambda minus 1 alpha mu lambda minus 1 beta mu d prime alpha d prime beta, right? And phi, which is a function of x, is transformed via some s, which we don't specify. It's s phi prime x prime. So what we know is what we need here is that this S is a unitary transformation such that S minus 1 S equal to identity. So we have here this property. And now we can just pick up the Klein-Gordon equation and study its covariance and see what is the condition on this S transformation. So picking up the Klein-Gordon equation again, so G mu nu d nu plus m squared. I guess that those that are in gravity, they may have noticed already that the sign here is plus.
Yes, and
Exactly.
now,
So
what the definition of the Lambertian is different?
the definition of the Lambertian itself is different, so, and it compensates basically for that. But just bear in mind, this is one of the places where this. So I guess you guys in gravity, you use the Klein-Gordon equation a lot.
In the exam, can I use the correct signature?
What is the correct signature?
Minus plus plus.
I will not object. You can use whatever
As
you.
long as I state in the beginning that I'm going to use.
Yes, that's something that I want to make clear to all of you. If you want to, at the level that you are working on, if you prefer to use one or another signature, just state that which signature you are using. If you don't state anything, I will assume that you are using the standard, the one that I use basically, the particle physics one. But you are free to use the signature that is better for you, that you can understand in a better way. Right. So now let's write down the transformations here. So it's pretty much just copying what it's above. So we are going to have here G mu nu on the minus 1 of mu on the minus 1 beta nu d alpha prime d beta prime plus m squared s phi prime, and this is equal to 0. Now, recall from the previous lecture, I still have the previous lecture here. Let me put it on the screen then. That we have shown this result here, that how is the Lorentz transformation of the metric. We just do the invert in verse 1 now, because we have this gamma minus 1. This is basically in terms of the matrices, it's the gamma beta entry gets a minus. So for you to put things in perspective, the inverted matrix is, I wrote it further down, apparently.
Yeah, I just saw it. Yeah.
Here, exactly. So basically what happened is that you are going to have a minus here and a minus here. That's basically the difference when you do the inverted. It's pretty much putting a minus here and a minus there, essentially. So back to today's lecture. So using that result,
Yes, because even physically, you can see that the other referential is going minus the velocity.
Precisely.
Only
Yes,
those things change.
precisely. It's when moving in one direction, you go to the other one and the velocity gets to minus. Exactly. So d alpha prime, d beta prime plus m squared s phi prime equal to 0. So therefore, what we have is here you have D'Alembert operator in the other reference frame plus m squared s phi equal to 0. So what is the condition for it to be a covariant? So this is the Klein-Gordon equation. If something happens to S, basically. So the Klein-Gordon equation becomes invariant under Lorentz transformations if the following property holds. If S, I forgot to put a prime here. Sorry, guys. S prime here, of course. So if S phi prime equal to phi prime, right? You agree, all of you? This means then that S is equal to S equal to identity. So now tell me, what is which type of transformation is this? Exactly. So it's a number. So it's a scalar transformation, indeed. So what happened is that it's like a number. The only way to transform a number is with identity. So there is no matrix operation or whatsoever that you do to transform a number, a scalar. So this means that phi is a scalar. Therefore, the Klein-Gordon equation only describes scalars. So it's an equation for scalar fields. Basically, the Klein-Gordon equation cannot describe, for example, relativistic electrons. Electrons, since phi must transform as a scalar, which is not the case of an electron. An electron is a spinor, in fact, so it does not transform as a scalar. Right, so it's an equation for spin zero. So let me put here. So this is for spin zero particles. And what are the solutions?
Well, the equation is an exponential.
Yeah, exactly. So, but the solutions, we want to look into the eigenvectors and the eigenvalues. So we want to look to both things. And that's, there is a,
Don't have a negative energy.
exactly, that's, exactly. So that's it, that's precisely where I want to go. So we have these ansatz, the solution ansatz, where phi x e to the minus I px, and this is just e to the minus I p t plus I p. It's just to set the notation. So we can just try this solution. So we put just g mu nu d mu d nu e to the minus alpha x alpha. In fact, it's mu here. I put the dot there, but it's okay. Plus m squared e to the minus I x mu equal to 0. And when you solve this, you just so you take the derivatives, or you just pass the derivatives into the momentum space, and you get like g mu nu. There is a minus I here coming from the exponential, minus I p mu minus I p nu minus I p alpha a to minus 1. So I just wrote these alphas here because if you expand this, when you go from here to here, you can take the derivatives, and you need to be careful with the indices there. So that's why I wrote this, because we are taking derivatives, these mu and nu derivatives, and therefore I had to write alpha here. And then when you do this, there is a Kronecker delta function that shows up there, and that transforms it back into mu's and nu's. But this is just to be consistent in terms of indices. Right, but this is no more no less than minus. So we have the g mu nu, so minus p mu, basically, p mu plus m squared phi, which is this, I'm recasting now phi by this exponential, this ansatz here, again, putting this, equal to 0, which means that what you get here you have minus e squared plus p squared plus m squared phi equal to 0. Then you get that e squared equal to p squared. Then we have two solutions, and this is what you may have been expecting to see, plus or minus p squared plus m squared. In fact, you will have eigenfunctions. You have two eigenfunctions, a certain basis, phi plus x, phi minus x, where phi minus, plus and minus stands for the positive and the negative energy, basically solutions. And this forms a complete basis. So you cannot simply remove one of these solutions. You need to have both. Because you write any state. This is something that you might remember from quantum mechanics, that when a basis is complete, it means that you can write, for example,
Anything as a superposition.
exactly, like C1 phi plus x plus C2 phi minus x. So a solution is a superposition of these two basis functions, and you need to take into account both. They are not removable, so you need to understand what are they. What is this in fact? And to do so, there is to understand what's going on. We are going to do here something which is like minimally coupling it to the electromagnetism. Let's minimally couple. So to understand the meaning, to understand the meaning of the negative energy solutions, let us couple the scalar field to an electromagnetic field.
I have a question which might be stupid, but
Yes.
why do we always
There are no stupid questions. That's the first thing.
why do we always couple one, for example, in a Klein-Gordon equation, we always couple the electromagnetic field to the scalar field minimally. Why don't we use powers of the electromagnetic field, for example?
And why should we complicate our lives?
Well, why should we do that?
It depends on what you want to do.
How do we know it's true?
Well,
That
we know that there are things that we measure, and we know how things happen. But this is, let's say, this is not the way one should do things. Is not simply let's minimally couple. And here I'm talking electromagnetic field, but this can be any field that behaves like an electromagnetic field, some vector field. The thing is, when you choose your couplings, and this is what you're going to learn throughout this course, and I hopefully starting not next week but the week after, is that you don't choose what to couple to what. You choose the symmetry, and the symmetry dictates what has to couple to.
In this case, the minimal coupling conserves the
Exactly.
gauge symmetry.
Precisely. And when you have two criteria. One of the criteria is let's define a symmetry and write all possible interactions that the symmetry allows. And the second is those interactions need to be renormalizable, because you want to have a complete theory. If you start putting non-renormalizable interactions, it means that your theory is not complete. There is something else, some UV completion. That's why the name of UV completion. That you need to have some considerations about. That's essentially what happened between the Fermi theory and then what became the electroweak theory. The Fermi theory is like an effective theory where you have 4 fermion interactions. But then when you zoom in, that is when you increase the energy, you go to the electric scale and you see that these 4 fermion interactions, they are exchanging W boson or Z bosons, and that makes up basically the complete theory. So you have all the ingredients of the theory in a way. So here, this is only a minimal coupling because our aim is only to interpret what is this negative. And we only need one ingredient. We need a charge. Because there is you see, so we only need a charge. We want to put a charge here because things become intuitive when you put a charge.
probability current to current to current.
Yes, yes, exactly. So, and we do this in the following way. We say that we have our A mu is equal to phi and A. So this phi is in fact like here in the, it's part of this vector field. And then when you do this minimal coupling, at the moment, I'm only going to say that this is how it is, but in a few, in some lectures after this one, we will come back to this again. So d mu plus I q A mu. So you need to change, this is basically going from the total derivatives to, or in this case, it's partial derivatives to a covariant derivative. But let's not now call it covariant derivative. Let's just say that this coupling implies this, because that's the thing. You need to keep invariance of the Klein-Gordon equation. In this case, it's gauge invariance. I'm not specifying symmetries, but there is a hidden symmetry here. And I need to put this, otherwise I would violate that symmetry. Say, Osvaldo, you want to say something?
Do you want to use phi for the scalar potential?
Exactly.
Yeah, this is just a.
No, but we are using phi as the wave function.
Yes. Maybe this is. Yeah, you are. I think you are right, because something. Yes, that this is not like the. And actually, this is written like that in the lecture. So this should be. Yeah, and I wrote a naught, and then wrote phi there. Yeah. Yeah. Let's just write a naught here. Yeah, good point. Good point. So let's go to the Klein-Gordon equation again. And so the Klein-Gordon equation is redefined in the following way. So G mu nu, and now we have d mu plus I q. Let me say q is the charge. Can be electric charge. If this is an electromagnetic field, it's an electric charge. I will indeed say this is electric charge. Let's make it concrete. Charge of phi, in fact. Of phi. So plus q a mu, and now d nu plus a I q a nu plus m squared, and now we have phi plus. So we are looking into only the positive energy solutions here. We know that both solutions obey a Klein-Gordon equation, so everyone is happy about it. And now we know that the negative energy solutions are the complex conjugate of the positive one. So that F minus is F plus. It's a complex conjugation. So we can complex conjugate this, and we get, so complex conjugation upon complex conjugation, we get G mu nu, d mu minus I q a mu, d nu minus I q a nu plus m squared phi minus equal to 0. So essentially, what we get is the only difference. So we can go from, let me put here, this is equation A, and this is equation B. We can go from A to B by basically inverting the charge. Of course, there is still the function, so the phi plus, you should, it's not only inverting the charge, it's not only inverting the charge, you need to do the charge conjugation, basically, the charge conjugation operation. So, but what I want to say, so to be in rigor, what I want to say is that, so phi minus, so the solutions with negative energy is the charge conjugation of phi plus with we have the charge of phi minus equals to minus the charge of phi plus. And in particle physics, sorry, a charge conjugation operation transforms particles into their antiparticles. So this is so we keep the properties of the particle. We didn't change the properties. So the mass is the same, the spin is the same. It's zero in this case, and the only thing that changed was the charge. So this is clearly so the negative energy solutions are the antiparticle of the particle, basically. And this is easy to see in the case of a complex field. If you were talking about a real field, so this operation would still be valid.
Superposition of the two solutions.
Exactly, precisely. It becomes a real. So the Q will be zero. You can still do this, but Q will be zero. But it's but what is it? What this is also saying is that the basically charged particles are complex. Charge scalars are complex. The charge is indeed related to the complex nature of the scalar field, because there is a phase, and the charge, an electric charge, is related to a phase invariance, which you will learn. We'll learn later on. Okay, this is all I wanted to say about the Klein-Gordon equation. We can now go to Dirac equation. Now let's go to Dirac equation. This will be a little bit more involved here and there. So the solutions of the Dirac equation are a little bit more complicated, but they are very interesting outcomes and things that will follow us to the rest of the course or the two courses. And that's why I want to discuss all of this. So now let's go into Dirac equation. All right, so Dirac equation, by the way, it was in 1928. 1928. So the Klein-Gordon equation was postulated in 1926 and Dirac in 1928. So it was really rich times, so in terms of scientific and all these developments in quantum mechanics and relativity, etc. Really good times. Right. So so Dirac. So his idea was the following. Okay. So Schrödinger equations. I want to describe electrons because I cannot describe electrons with the Klein-Gordon equation, and I can describe non-relativistic electrons with not talking about the spin, but I can describe non-relativistic electrons with the Schrödinger equation. which is an equation that is linear in basically in the time derivatives. Essentially, so the Schrodinger equation, I will write it again. So we have I d dt of a certain state equal to certain Hamiltonian psi. This is our Schrodinger equation again. And we know that one of the postulates of quantum mechanics indeed tells that that the evolution of a certain state. So that's why I wrote this with a cat, because now I'm really talking about the state. It's given by by this basically by this equation. This is how you time evolve a certain state. Right. But what the hypothesis of Dirac is that let's have this time derivative here. One, not a second, like second derivative as we have in Klein-Gordon equation that you have here. This is a second derivative. Sorry, here, the second derivative. Let's keep it as a time derivative, and also let's make it relativistic. So what he said was that maybe my Hamiltonian is a linear combination of some alpha times momentum plus some beta times the mass, where alpha and beta are Hermitian operators. They have to be Hermitian operators so that you preserve the hermicity of the Hamiltonian. So now we can put this all together. So if this is our Hamiltonian, we can say that this alpha in turn p dot p plus beta m, and you add this on a given state. This is the energy, and I will write energy squared. So I'm adding twice this Hamiltonian, basically. This is the energy squared. And what we can see from here, so we know that this is a relativistic theory. So this is a relativistic theory. So we should write that this alpha dot p plus beta m squared, this has to be equal to p squared plus m squared. And if you just basically expand, if expanding the left-hand side, you will conclude here that we'll conclude a few things. Maybe I should write so that you can visualize it here. The expansion is not extremely big, so on one side you have alpha dot p squared plus n, and now we have alpha beta plus beta alpha. This quantity is not necessarily commute. That's why we have to write like that. Plus beta squared m squared, and this is equal to p squared plus m squared. So what can you take from here? So you can take a few important things from here. So from here we can take that alpha dot p squared, this has to be equal to p squared. This is the first condition. The second condition is that this element here in the middle, this has to vanish. This will define an algebra. This is quite nice because this reasoning is defining an algebra. Alpha beta plus, and even more so, an anti-commuting algebra equal to 0, and our beta squared has to be identity. I will write 1 for now. So, and we can basically, these ones are obeyed if basically if we write the following. So we know already, so beta squared equal to 1. Now alpha squared, so if you pick up the first one, so from the first one, but alpha I squared equal to 1. Basically, what's happening here is that you are doing the following here. You are saying that alpha p squared, this is equal to alpha 1 squared p1 squared plus alpha 2 squared p2 squared plus alpha 3 squared p3 squared, and now cross terms alpha 1 alpha 2 p1 p2 and so on. And you want, because you want this to be equal to p squared, so this product here, so the of this with the same I, this has to be 1. Likewise, beta squared is equal to 1. But you also take from here that when you have a product of alpha 1, alpha 2, you have it has to be 0. And also you have already this condition here that is 0. So you extract the following as well. So this gives rise to that, and then alpha I beta plus beta alpha I equal 0.
Just one question. Doesn't it follow that the cross terms that when you apply alpha 1 by alpha 2 must be 0?
So say it, sir, again. I don't see what
The
you're
cross
saying.
terms must change.
Yes.
So doesn't that mean that alpha 1 and alpha 2, for example, must be 0, their product?
Yes, exactly. And this is the third condition.
Okay.
Alpha I, that's precisely the thing. Alpha I, alpha j. But then you need to take into account that you have like P1. So alpha 1, alpha 2 is not the same as alpha 2, alpha 1, let's say, in principle. So alpha j, alpha I equal to 0. What we were saying is this, and this is for I different than j. And of course, I and j equal to 1, 2, 3. That's exactly what we were saying, but just take into account that we need to consider this, the algebra, and that these are operators. So we should not assume that they commute. Right, great. Now, this means that we can further write the Dirac equation in the following way. So now let's go again to this equation. So and take now let's write it in terms of partial derivatives as we have been doing. This is the evolution. This is the evolution of a state. This is simply a postulate of quantum mechanics. So now let's write the Dirac equation taking in terms of partial derivatives. So our I dt psi, this is going to be alpha dot p plus beta m psi. And now we can use the again the fact that that p equals to minus I at the gradient. So I dt psi is going to be beta. Yeah, I can simply write this minus I alpha plus beta m psi. This is a dot here. Right, because we are using the fact that p equal to minus I gradient. And now we can multiply by beta. Recall that we have some properties here that we can make use. We have this property that beta square is equal to 1. So we can rewrite this in the following way. I beta dt psi is going to be equal to minus I beta alpha gradient plus m, because here it's beta. I'm multiplying beta on the from the left basically. So beta is identity, and we can define beta equal to gamma 0, something that we are going to call gamma 0, and this beta alpha to gamma. And it follows, finally, that, so then, I gamma naught d naught psi, it's equal to minus I gamma I di plus m psi. So we can put it, bring it all to one side. Let me just see something here. So you see that you're here gamma naught d naught and gamma I di. So you can write something like the final form of the Dirac equation, which is I gamma mu d mu minus m psi equal to 0. And this is basically Dirac's equation and the form of the Dirac equation that we will use throughout these courses, basically.
No slash notation?
Oh yeah.
I think I will not use. Maybe if it's really necessary, you can write this like this as well. Oh, what did I do here? You can write this way if you prefer. Here d minus m psi equal to 0. If you prefer to use the slash notation, basically. So basically, gamma mu d mu is slash. It's what Oswald was saying, and this way we have defined a new four vector, which is gamma mu, which is gamma 0 gamma. And this
Could we say that gamma is truly a 4 vector because it must transform differently. Not to compensate the C that's not going to transform the scale as a scalar.
What? So you asking if the way it transforms, I mean the gamma mu, the way it transforms, but why does it not transform as a 4 vector?
Because the wave function also transforms differently.
Yeah, this wave function is not a 4 vector, indeed. It's not. But here you are talking about two different spaces.
Yes.
This, if you want to put it in terms of indices, you have a color that can be seen here. Okay, it can be here. So alpha, you have there is a spinor index here,
Yes.
alpha, right? But you also have here in gamma mu.
Oh, okay. Considering only one component of the spinor, this is a scalar equation.
Exactly. Alpha, beta, and there should be, so what is missing here?
It has to come.
Because this is a 2 by 2 matrix, yes. Of course, there is here an identity. And I'm missing the second index, which should be somewhere here. This is 4 by 4. This is spinor. So there is there's a U factor here. Of course, but this zero is also alpha or beta if you prefer. And if you put here alpha beta, sorry, if you want to multiply it by alpha. But the thing is,
alpha beta.
The thing is, this zero is like this.
Yes.
Basically. So there is one index that is hanging out. So and you have this alpha. You just need to do the matrix multiplication here, but there is
alpha beta and C is beta.
Exactly.
Beta and 0 is alpha.
Alpha beta, and 0 is alpha, something like that. And alpha goes from 1 to 4. So, but that's to say that
no, actually alpha should go from 1 to 2.
No, alpha goes from 1 to 4 or 1 to 2, depending on which type of spinners you're talking about. Here, I'll be talking about Dirac spinners.
Okay.
At the moment, I will not go into while spinners for now. Yeah, and while spinners, indeed, they are two. Exactly. This has both at the moment. I will just remove the indices from here because at the moment it's not. This is not. We can write in condensed notation, and we will use the indices surely in a short while. So, of course, now it's something that I'm not going to be here redefining all the algebra. But what happens is that when you pick up this algebra that you define here, so you pick this up. Let me also say that this is also equal to beta squared here. And from here, you can just rearrange, play with betas, putting betas on the left, betas on the right, and you reach a point where you have gamma mu equal to 2g mu nu. So this is not ending exercise, but you should just show that this is possible. Actually, I have in the notes I have this done. I found a lot of typos in the notes, so you should always have some critical looking here in this particular steps. I didn't, but this is it's good that if you can pick up these conditions that are here, this one's here, sorry, not this one's here, and show that from here you can get to here, basically. And this is called the Clifford algebra. A Clifford algebra. And it's also interesting to note that we can make products of these gamma mu's matrices and find something that is, for example, we know that. Let's do some counting here. We know, for example, we have that gamma 0 squared equals to gamma I squared, which is identity. So here we have one component. So this is one matrix. So one component. One component. Now we can define a new matrix, gamma 5, right? Which is equal to I, gamma 0, gamma 1, gamma 2, gamma 3. And once again, in the space of these matrices, this represents again one vector, say one component, one basis vector. I'm already talking about the basis because I want to lead to something. One component. Now we look into gamma mu, and these are there are 4 of them that are independent, right? So here we have 4 components. In fact, there is a combinatorial, I think it's out of these matrices, if you have like a combinatorial of the 4, the thing here, 4 kappa. If it's 0, if it's 4 0, it gives 1, which is where you don't have any combinatorics to do. But if you have only this, actually this is, I think this is in a book which is Carlo Giunti. This is just I want to let you know that there is a more combinatorics explanation of this simple counting that I'm doing here. And the details are in this book, the Carlo Giunti book that I've shown you. So see, I will put here C Giunti. Because he has a combinatorial formula to get this in rigor, basically.
And now the components of the matrix themselves are matrices which are the Pauli matrices. Right?
Yes, yes,
matrix, but
yes, exactly. I will come to that as well. So we have now this gamma mu, gamma 5, and once again this has 4 components. Essentially, you can count the components by looking into the independent ways of mu that you have of using mu here. Essentially, when you have like the first and the second line, you have like 0 independent ways, basically, of using mu, because mu is not even there, and that's in the combinatorial. Exactly, if they are scalars. That combinatorics that I wanted to put here, like 4 kappa. Sorry, it's made 4 by 4 matrices, and this kappa is the way you have to combine those matrices. If they are scalars, you say this is 0, this is 4 0, and this gives 1. So when kappa this is equal to 1, if kappa equal to 0, it's going to be equal to 4 if kappa equal to 1, and kappa equal to 1 is when you have like mu or mu times gamma 5. Basically, you only have one mu to play with. But there is one last possibility, which is what we define as sigma mu nu, which is defined as I over 2 gamma mu gamma nu. So this is antisymmetric. The sigma mu nu is antisymmetric. And so what is the possible combinations that we have of an antisymmetric matrix, a 4 by 4? So how many combinations of mu nu we can have in an antisymmetric? So basically it's like 4, 2 here. It's the binomial form 4, 2. So essentially you can think of a matrix, a 4 by 4 matrix, because mu nu goes from 0 to 4. Yes, do the counting. Precisely.
6.
Exactly, 6. That's it.
There's a formula.
There's a formula.
Never.
I'm only counting. I'm only counting here, but there are 5. And that formula that you are saying, if I'm not wrong, Marco, is n minus 1 over 2. Does it work?
Yes.
For n equal to 4, it's 6. Yes. For n equal to 4. Yes. 4 times 3, 12 over 2, 6. Yes. So this is the number of possible independents. Okay, but this is it. We cannot go beyond this. Let's say if you put products of more matrices, this is like a closed set. So when you put products of more matrices, that's a reducible. That would be a reducible. Let's say a reducible vector or a reducible representation. Exactly. So you would repeat. You can always cancel with something else. You can reduce to 4 or less components. You can always do that. And if you have different combinations of these matrices here, for example, if you put gamma 3, if you alter the order of these things, it's just up to plus or minus signs because of the algebra, of the Clifford algebra of this here, and therefore those plus or minus signs they would not affect the basically our space. And the space that I'm talking about is that with this you can build a basis. These are now you can sum 1 plus 1. So here of 6, so 8 plus 6 plus 2, 16, right? So here, summing all of these independent possibilities, you have a dimension 16 basis, which is given by the identity gamma 5, exactly, gamma 5, gamma mu, gamma 5, and sigma mu nu. These are 16 independent vectors here. Is it clear for everyone? So these are 16 independent vectors here. And then you can write, so these are 16, what does it mean? That you can write, so a 4 by 4 matrices have 16 components. So you can write any generic M, so any M 4 by 4 as like M1 identity plus M2 gamma 5, where M1, M2, M3 are simply scalar numbers. M3 gamma 1 and so on. Plus M, let me write here, M16 sigma 2, 3. Right. So this is what how we can write any generic 4 by 4 matrix. And just to make things concrete, and as Mark was saying, let's write these gamma matrices in terms of the polymatrices and so on. And this is going to be important. There are different representations that we can use. So we can use the Dirac, the Pauli Dirac representation. So the gamma matrices is can be expressed as so one of the possibilities is the Pauli Dirac representation. And in the Pauli Dirac representation, we have gamma 0. It's basically diagonal. Gamma I, and this is going to be important in the calculation of the solutions of the Dirac equation. And gamma 5 is going to be equal to 0, 1, 1, 0, right? And the Pauli matrices, you know what they are. So these are the Pauli matrices.
We just use sigma for the gamma matrices.
You use sigma.
Come to take out the gamma matrices, broke it up.
Sorry. You mean this sigma mu nu?
Yeah.
Yeah, this sigma mu nu. But this sigma mu nu is also written in terms of the sigma Pauli matrices.
Yeah.
You just have.
Okay. So it's just,
But this is
the
sigma mu nu. Well, it's but sigma. But this is the notation basically. But the thing is, since you have two indices here, you don't confuse this with the Pauli matrices. That's the thing. But this is indeed the textbook notation. There is another representation. This Pauli Dirac representation is the one that we are going to use in what follows. But there is another representation, which is in fact more convenient when you are doing particle physics calculations. When you go to more realistic context. Another possibility is the while or the chiral representation. Chiral. It's called chiral representation or while representation because gamma 5 is called the chiral matrix or the handedness matrix, let's say. And what the chiral representation does is, for example, gamma 5 chiral, C of chiral, is equal to gamma 0 D. So it becomes, you basically flip the definition here.
Gamma 0.
Yes, gamma 0. This is here, it's gamma 0. And the chiral representation of the I is the same as in the Dirac. So these ones are identical. But then you have to put, so the gamma chiral 0, the gamma 0 in the chiral representation is equal to minus gamma D5. So in fact, what you get is this. Gamma 0 chiral equal to 0 minus identity here, minus identity 0. It's that one there. Gamma I chiral, right? It's the same, 0 minus sigma I minus sigma I, and this is without minus here, and 0. And we have gamma chiral 5 equal to 1, 0, 0 minus 1. And Oswald, as you were saying, so look at what is the thing here, is that with this, well, this is not exactly the sigma mu nu, but with this representation, you can write something like gamma mu c equal to 0, and now sigma mu, it's yet another sigma. This is what I wanted to say. This is yet another sigma. Minus sigma mu, and here sigma mu bar 0.
This bar means what?
Means the following.
These are not the polymatrix.
These are not the polymatrix. These contain the polymatrix. This is like a 4-vector extension of the polymatrices, essentially. Oh, what's happening? Here, did I stop sharing?
Yeah.
Okay. So sigma mu is basically minus identity sigma mu bar, and sigma mu, since we have this minus there, it's simply 1 sigma I. See, right? And this is not sigma mu at all. So, but there are sigmas everywhere here. So we are going to be using, for the moment, for the time being, we will use the poly Dirac representation. So basically, in what concerns determination, the calculation of the solutions of the Dirac equation. So let's go back to Dirac's equation, and we have, so let's write again the Dirac equation here. I gamma mu d mu minus m psi equal to 0. Just to have things in front of us. And now we know that psi, as we were discussing, in fact, this psi, this is a 4-component spinor. Say. So this psi can be as index alpha, as we are saying, and we can the actual spinor. This is the wave function. Let's say the actual spinor is something that we call u, which is a function of the momentum. And now we have the exponential part, similar to what we did to the Klein-Gordon equation. Minus I p mu x mu. So this is basically expanding this to write in terms of the u spinors. So clearly you have now d mu alpha, d mu psi alpha is equal to minus I p mu psi alpha. We are going to use this, which means that because now we can replace, we can basically trade this the derivative d mu by this p, and rewrite the Dirac equation in the following way. Without I. Gamma mu, p mu, or p slashed if Osvaldo prefers. Gamma mu, p mu, minus I m u alpha, p, equal to 0. So this is an equivalent. This is equivalent to the previous. The minus has disappeared because you have the minus I times I. essentially. So Osvaldo was asking where the hell is well, he asked, isn't there a minus here? No, because you have minus I and I here. Right. Now, we can multiply. Let's now rearrange these things. Let's see what are the energy. What is the energy of the states of the Dirac equation? That you know the answer, but let's recall that. So multiply on the left by basically gamma nu p nu minus m. And doing so, we get the following. Gamma mu, sorry, I cannot. Gamma mu, p mu minus m squared u alpha p equal to 0. Now, what is this? What is this term here? Now, the question is, what is this? So, what is this?
Just one thing, should
Yes.
we be putting the alphas on the matrices too?
Yes, because we have. Let me think. Yes, because we have. This is a spinor. We are just putting. There is this. This.
It's understandable.
We don't have to keep it. I say we don't have to keep it around. But it's the thing is we are putting here and we are not putting in gammas. You know it. So there is an imbalance. In that sense, there is sort of an imbalance indeed. If we can eventually put also on gammas and then all would be fine. But this is just to signal that this is not essentially. This is to say that that there is this matrix character of the mu. But and the thing also here is that you have so you have the alphas and betas, the indices on so beta prime, and here you have beta prime alphas, and yeah, because then you have to well, you don't contract with alpha because this is at the end you have this but things get more confused. The thing is, this is a vector. This 0 once again is like are 4 zeros.
Yes.
But the thing is, not putting alpha, so we know this is a spinor. In a way, it's more. There is not this imbalance, and we don't have the risk of being here having this difference. So yeah, I can drop the alpha. That's a fair point. So to get this, to see what is this, we can use one of the results. So we have our so 1/2 gamma mu, and multiply this by p mu. And this is, we know that this 1/2 gamma mu, this is equal to g mu nu times, I just revert to the order compared to what was here. So gamma mu, and g mu nu, that's okay, g mu nu, and now p mu, right? And this is, we can now expand the other one on the other side. So 1/2, and this is an anti-commutator, so it's gamma mu gamma nu minus gamma nu plus gamma mu, p mu is equal to p nu. This is simply the e squared minus p, right? So we can further expand this and have 1/2 and now gamma nu p mu plus gamma nu p mu equal to e squared minus p squared here, right? Now we can also put, we have the freedom of commuting the momentum, both momenta. So this is 1/2 gamma nu, and we can put p nu, right? So let me just signal that we are doing this here. Yeah. Plus gamma mu p mu. And now you see that here you have two independent sums with dummy indices which are the same. So this is equal to that. So both sums give the same thing. So this is equal to gamma nu p nu, because it's sum of the 1/2 cuts the 2 that shows up there, and this is equal to e squared minus p squared. So this is what we want to plug basically here in this question mark. And plugging it there, what we get is the following. This means that e squared minus p squared minus m squared minus m squared u equal to 0, or e squared minus p squared u equal to m squared up. And from this, we can have a first solution of Dirac equations, but let's consider the rest frame. It's the easiest one. And for this time, it's best to discuss only the rest frame one. And we start with the lab frame in the next lecture. So, if the particle is at rest, so if the particle is at rest, what we have is the following. We have e squared, basically, right? E squared u, and here let me put u alpha here, because we will start using matrices now. And of course, we need this we need an identity matrix here as well. So it will be alpha equal to m squared identity u alpha p. which means we see immediately that the energy equal to plus or minus m. So once again, we have negative energy solutions, but we already know we are going to use the same, that these negative energy solutions are the basically the antiparticle. Dirac had a different interpretation back then. I guess you have heard about the Dirac sea, and basically he thought that all negative solutions were filling like what we call the Dirac sea, a ground state. So negative energy was lower than positive energy, and because of that, that energy was more favored, and it was completely filled. And because of the Pauli exclusion principle, you could not have like a positive energy solution following into the same quantum state, let's say, but with negative energy. So what happened is that for his interpretation, if you excite this Dirac sea, one of these electrons of, let's say, electrons of negative energy would be excited and would form this pair with a positive energy one.
Like in semiconductors.
The Cooper pairs, yeah, exactly, these sort of things. Yeah, that was his interpretation. And that was also a good the primordial interpretation of the electron-positron annihilation and so on, because they were already seeing this sort of phenomena, but didn't associate to an antiparticle. But this works for fermions and for Dirac equation, for electrons, because you have the Pauli exclusion principle, and you know that you cannot populate these negative energy solutions, which were favored. So it was that lower energies were favored. You could not fill that with the positive energy ones. But for the case of the Klein-Gordon equation, this was a big fail, because for scalars there is not the exclusion principle, and yet you don't see these negative energy ones. So in fact, it was when you excite one, the hole that was left there was was perceived as a positively charged electron from Dirac's interpretation. But this is no longer what we know. We know this is a positive energy antiparticle. That's what we know, with the opposite charge and so on. But now what we have is that using the Hamiltonian, so when you have HU alpha equal to gamma 0 M U alpha, so you can write, you know that energy is positive and negative energy, and based on this, we can write the solutions, or the Dirac equation, in the following way: E 0 E, and this is identity. This is in a 2x2 condensed form. U alpha equal to M 0 minus M1, essentially. And the solutions here are quite trivial, in the sense that you have, for example, U1. If you have this basis, U1 1 0 0 0, U2 0 1 0 0. Once again, this is in the frame, in the rest frame of the particle. U3 0 0 1 0, and U4, let me this. And U4 0 1, right? Where these first two are the solutions of positive energy, and these two are the solutions of negative energy. But what do you guys note here immediately? There is something here that strike our eyes immediately when you look into these solutions. Can you guess immediately? So how many positive and how many negative energy solutions do we have? We have pairs. So there is here a double degeneracy, right? So these solutions are degenerate. So it means that there should be something else encoded in this equation that can distinguish between the states with degenerate energy. And that is in fact spin. That is where spin, so this is like to say that spin is emergent directly from Dirac equation. For example, and this is embedded in these gamma matrices. If you do this external product, so if you do you reach the following conclusion. This is going to be equal to minus 2i sigma 1. So I'm already writing the result here. Sigma 1, 0, 0, sigma 1, minus 2i, sigma 2, 0, 0, sigma 2, minus 2i, sigma 3, 0, 0, sigma 3. And this is a vector, so there is, and this is E1. Here it's E2, and here is E3. And this is no more, no less than, so if you define S equal to I over 4 gamma, this way. Yeah, so this means that, which is equal to Sx, x plus Sy, Ey plus Sz, Ez. So in fact, these are the Pauli matrices here. Let me just, for consistency of notation, just write x here, y here, and write z here. So you see, the spin is embedded in this, and the nice thing is that this S, the important thing here, and to finalize, is that S and the Hamiltonian, they commute, right? So these are compatible variables. Thus, U1, so these solutions, U2, U3, U4, I could just have written UI. Look that this is not the alpha index equal to 1, 2, 3, 4, or 4. This is just the solution 1, solution 2, 3, and 4. There is still in this half here. Thus, is also is a basis that where go why is this the Hamiltonian and S simultaneously. So in the rest frame of the particle, the solutions of Dirac equation are also eigenfunctions of spin. So, and if you apply this to basically what you see, if you apply the SZ, basically, if you do SZ to U1, 3, you get like 1/2 U13. So this is the spin up solution, and SZ applied to U24 equals to minus 1/2 U24, which you can easily do but just by that's trivial, just applying the Pauli matrix to these solutions, and you get the eigenvalues out of it. So, and you see, this lifts the degeneracy. So this happens that, to conclude, U1 is particle solution E equal M, and SZ equal to 1/2. U2 is a particle solution with positive energy, but SZ equal to minus 1/2. And U3 is antiparticle solution with positive energy or negative energy if it's a particle solution, with SZ equal to 1/2. And finally, U4 is a antiparticle solution with positive energy and SZ equal to minus 1/2. So the spin, so the degrees of freedom that the Dirac equation encodes contain automatically spin. And this is one of the very pretty things about the Dirac equation. But this is, we will stop now, but let me just say, as a prelude to next lecture, where we're going to finish with this, we are going to start the Lagrangian formalism, but before that, we will see what happens if we are not in the rest frame. And you realize that the spin is no longer commutes with the Hamiltonian, and we need to define a new operator to play the role of the spin. And that is what you, does anybody know what I'm talking about, or has any idea? You are reaching the point, exactly. It's the helicity, in fact, but from the helicity we also go to the chirality. And there will be, for next lecture, and now I want to say to everyone else online, that there will be a exercise. I will give an exercise for ending for evaluation, but it's going to be about this subject, which you can solve and end in the week after. So, but I will give you next week because I have not yet covered the topic fully. The topic for that.
We don't need to solve it for next week.
No, not for next week.
Okay.
You only have to solve that later, basically for in 2 weeks, more or less. We can discuss that next week. So it's only going to be Thursday. So it's not going to be before Thursday the week after. Okay, guys. So I conclude here. Is everybody online? Does anybody want to say anything? Okay, I don't think so. Everyone is here. I will stop.